Alright, we're gonna finish off our limit video here today. So this is our last topic for our first unit, and this leads us into derivatives. So what we're gonna look at today is how we can calculate limits for secant lines, for tangent lines, and also normal lines. So you can see on this picture I've got here, a secant line is any line that connects two coordinates on a graph. So it doesn't matter what the graph is. If we have two separate coordinates, we can figure out what the slope and the equation of that line would be. The tougher one is what happens when we have a tangent line. So you can see a tangent is a line that just touches in one location. And not only does it just touch in one location, but it actually touches perpendicular to the normal. So if I drew a normal line on here, that would be the line that's perpendicular to the surface at that location. So normals and tangents kind of work the same, just one's perpendicular to the other, and the secant line again is for any two coordinates. So if you think back to even Math 10 is probably the last time you looked at slopes of linear lines, we can use that formula to help us figure out how to calculate slopes. So in Math 10 we said that if you have two coordinates, we could calculate the slope of a line between those two coordinates. So really what we're doing is with any kind of graph is we're trying to figure out the slope of a line, which was rise over run. Right? What's the vertical rise divided by the run of that distance, that horizontal distance. So if you go back to that picture I had, we could just basically count rise and run if it was on a nice graph and you had nice coordinates and grids. Otherwise we would just use the coordinates. So for example, if I said, like based on that one that we had on that previous page, let's suppose that we had a coordinate at 1, 1, and let's suppose the other coordinate was at 3, 4, or something like that. So we wanted to figure out the slope of the line between those 2 points. We could just subtract the coordinates. So on the top we'd have 4 minus 1, and on the bottom we'd have 3 minus 1. So in this case our slope would be 3 over 2. So our rise is a rise of 3, a run of 2. Our slope would be 3/2 or 1.5. And remember, if our slopes go in that direction, that's our positive slope, and if they go downwards to the right, that was our negative slope. And a slope of 0 was a flat horizontal line, and if we have a vertical line, we either says it had no slope, or we could say it's infinite slope if we want to get technical with that. So secant lines, pretty straightforward. Just calculate your rise over run, or your y2 minus y1 over x2 minus x1. So that's sort of the formula that we're going to start with. So let's use that formula to see if we could figure out how we could use that to help us figure out a tangent slope. So if our equation is y equals x squared minus 2, let me just kind of sketch this out. So x squared minus 2 would just be a regular quadratic opening upwards, something like that. It would be down at -2. So could we figure out the slope between x of 1 and an x of 2? So what I'm saying is, what would the slope be between those two dots? Something like that. So let's figure it out. So if we plug a 1 into the equation, so when x is 1, let's write it like this. Let's write f of 1. Plug that into our equation, we get 1 squared minus 2, which is -1. Plug 2 into the same equation, 2 squared minus 2 would be 2. So now we have our coordinates. So our slope would be y2 minus y1 over x2 minus x1. So our y2 in this case, let's use the coordinate 2 that we have there. We got 2. y1 was -1. And our x2 was 2, and our x1 was 1. Doesn't matter what order we do these in, but let's just kind of call this one x1 and y1, and this one would be x2 and y2, and so on. So if we simplify the math for this, we get 2 minus minus 1, which is 3, 3 over 1. So in this case, our slope would be 3. So the way I sketch this graph out, let me just kind of show you that. A line connecting those 2 points would have a slope of +3. So we can do 2 points, but the idea is how can we only do 1? And it's a tough calculation because we need 2 coordinates to use the slope formula. But what we're going to do is, could we make that distance smaller and smaller? So if we kind of figure out what the slope is between 2 coordinates, but we make the distance between them infinitely close, we should have a pretty good answer. So let's try it again. So for the second example, we still have 1, so we already knew that that was -1, but what's it going to be now when x is 1.5? So if we move it down from 2 to 1.5, we're going to get a slightly different answer. So 1.5 squared is, what's that, 2.25, I think? Yeah, and take away 2 gives us a quarter. So if we do our slope calculation for this one, we're going to get a quarter, take away -1 on the top, and 1.5, take away 1 on the bottom. So that gives us 1 1/4, or 1.25 on the top, divided by 0.5 on the bottom. So that gives us an answer of 2.5. So what I just sketched out there now, or what I just calculated, was if we move this coordinate closer, right, so we're going to get this point down lower, so now we actually have a slope of 2.5 between those 2 points, so it's not quite as steep. So that's going to be a little bit more accurate than the first one that we did. So we could keep making this distance smaller and smaller and smaller, and eventually we should get it really, really close. So let's try one more calculation where we do still at 1, so that was at our -1, but now let's try it when our x coordinate is 1.01. So they're only 1/100th apart, so this one should give us a pretty accurate answer. So if we go 1.01 squared and take away 2, gives us an answer approximately of 0.097. So if we do that calculation now, so now we have -0.97 minus -1 on the top, divided by 1.01, take away 1 on the bottom. So I'll just quickly do this on my calculator. So we end up getting a slope of 2.01 if we type in all those decimals completely. So 2.01, you can see, is going to be even better yet. So based on our graph, now we have our coordinate that was at 1, one that's at 1.01, so it's a lot flatter yet. So we're getting it closer and closer to what it actually should be. And my graph isn't very accurate, but hopefully you can kind of see the point, is our slopes are changing less and less. So if we were to actually look at this graph, this green one that I just drew would be a pretty close tangent line. So at that location, we're going to figure out what the slope is just at x equals 1. So what we're going to try to do now is, can we do this in terms of a limit? So the idea is, if we make the second coordinate really, really small, so we just did it as 1.001, so our distance between them was just 0.01, but if we made it even smaller yet, if we made it 100th or 1,000th or 1,000,000th, that should get it even closer. So what we're going to do is, we're going to say, can we figure this out with just adding on a little tiny bit, and let's just call it h for argument's sake. So we'd still have f of 1 equal to -1, but now our f of 1 plus h will be slightly different. So we'll have 1 plus h squared, take away 2, that'll be our sort of simplified version, and let's even simplify that even more. Let's FOIL it out. So that'd give us 1 plus 2h plus h squared minus 2, so that would simplify to h squared plus 2h minus 1. So it's kind of weird algebra, but it actually is going to work out nicely when we put it in our formula. So now if we do our rise over run formula, we'd have h squared plus 2h minus 1 for the first coordinate. Our y2 was minus 1 again, so we go minus minus 1. And on our top we'd have 1 plus h for our first part, so this was our first coordinate for the top and the bottom, and then our 1s and -1s were our second coordinate. So all of this, if we simplify it, I'm running out of room, but I'll try to squeeze it in. We'll get h squared plus 2h on the top. The 1 and the plus 1 would cancel, and on the bottom we have 1 plus h minus 1. The 1s would cancel. We just get h. So we can even cancel out an h even further. We would just get h plus 2. So when we get, in terms of algebra, our limit is going to be at between x of 1 and 1 plus h, we get a limit of h plus 2. So our next step now is, could we figure out what the slope is going to be as the limit, in this case, approaches 0. So if we make that h infinitely small, we get that distance basically as small as possible, then we'll have our actual slope of one coordinate. So if we do the limit as h approaches 0 of h plus 2, you can see now we could just plug a 0 in, we get an answer of 2, and we're done. So what we can confidently say that is for this equation, if we went back to the original equation, and instead of me saying find the limit of a secant line, we could actually now calculate the limit of a tangent line. So for this one, our original graph was x squared minus 2. We tried to figure out what the limit of that was as it approached 1, and we did from 1 to 2, 1 to 1.5, and all these different things. But using what we just finished off, we can say the limit of x squared plus 2 as x approaches 1 is going to be 2. Sorry, I said that wrong. Not our limit as x approaches 1, we're saying the limit of the tangent line, or the slope of the tangent line, is going to be what the value we're looking for. So the limit isn't what we're looking for, because if I said what's the limit of 1, we just plug it in and we get an answer. So what we're saying is the slope of the tangent line, so the slope of the tangent at x equals 1, the slope of the line would be 2. So that's what we just calculated by doing all of this. So our goal now is, how can we do this more efficiently than what we just did? So let's go through the formula, how the formula is derived. And we basically just did it with that last example. So when we calculated the slope, we used y2 minus y1 over x2 minus x1. We plugged in numbers, so we had different coordinates originally. But our very last example, we did a coordinate and then we went plus h. So we're just going to keep it generic. So you can see that if we want to solve our slope formula between x and x plus h, let's call x the x1, and let's call x plus h the x2. So to get those y coordinates, we'd have to plug it back in the original. So we'd have f of x, and f of x plus h would be our y1 and y2. So now if we plug those into our formula, you can see it's a little bit complicated, but we're just still following the same thing we do with numbers. So we'd have the y coordinate, which is f of x plus h, take away y1, which is f of x, and then we'd have x2 minus x1, which is x plus h, take away the x. And if we simplify the bottom, you can see the x's cancel. So our formula should simplify to f of x plus h minus f of x divided by h. And that's going to be our formula that we're going to use to help us calculate the slopes of tangent lines, or the slope at one specific coordinate. So for this first example, what we're going to look at is just applying this formula. So we said our formula for the slope at a coordinate was f of x plus h minus f of x divided by h. So we're going to kind of do it for this case just to kind of see how the algebra would work. So we're going to call x1 2, and then we'll call x2 2 plus h. So let's figure out what y1 would be. So if we plug 2 in, we get 2 squared minus 6. That gives us negative 2. And our y2 would be 2 plus h squared. So I'll have to write it out. We'll get, here, we'll go 2 plus h squared minus 6. And let's simplify that. So we get 2 squared, which is 4, plus 4h plus h squared. Once we FOIL all that out, still take away 6. So this should simplify to h squared plus 4h take away 2. So that's going to be our y2 value. So if we plug that into our formula, so we'd have our h squared plus 4h minus 2 on the top for our first coordinate. y1 is negative 2, so we'd be subtracting negative 2. So you can already see that those are going to cancel. Right? The negative 2's would cancel out of both parts. And then on our bottom of our fraction, we'd have just h, because our x2 was 2 plus h, sorry, and we'd subtract 2. So again, those 2's cancel once again, which makes it nice. So all of this should simplify to just h squared plus 4h over h, and we can cancel out one of the h's. So you just get h plus 4, and the h on the bottom would cancel. So our slope between these two coordinates, I shouldn't have wrote it down below, but it'll connect here in a second. So our slope between these two coordinates is h plus 4. So the idea is if we can get that h value infinitely small, we'll basically in essence have the slope of a tangent line, or the slope of a coordinate when we only have one point. So in this case at x equals 2. So the only thing we do differently now is once we figure out what these slopes are, we do the limit as h approaches 0. So once we simplify it, you can see it's super simple. Plug in the 0, we get an answer of 4. So for this graph, if we went back to the original equation, and if I sketch it out, it would look like something like that. So what we're saying is add an x of 2, wherever that 2 would be, it's down here somewhere. The slope of that line would be 4. So it's a pretty handy way to calculate the slope at any given point. It takes a little bit of algebra and foiling things out, but it'll always work out to a pretty nice, easy limit. So let's do, we already did it when x was 2, so let's try it now when x is 4. So we can do it just like we just did. So we did when we did an x1 of 2, and we just did a y1 of 2, so this one gave us a slope of 4. Let's try it now when we have an x of 4. So our x1 would be 4, our y1, sorry, would be, if we plug 4 in, we get 16 minus 6, which is 10, and we should be good to go. So let's do, let me rewrite out the whole formula here. So we'll do the limit as h approaches 0 of f of x plus h, take away f of x, all over h. So let's plug in our algebra and see what happens. So f of x plus h will be, if our x is 4, we're going to be trying to figure out what is f of x plus 4, take away f of 4, all over h. Now we just got to do the algebra, so plug in x plus 4 into the original equation. So x plus 4 squared, so you'd have, I'll write it like this, we'd have x plus 4 squared, take away 6, f of 4 we already figured out was 10, so I'll just put that in, we don't need to rewrite that. So now all we got to do is simplify the top, so let's FOIL out the top, we get x squared plus 8x plus 16, take away 6, take away 10, all over h. What am I doing wrong here? Oh, I see what I did wrong. I wrote it as x plus 4. It should have been 4 plus h. Sorry, I'll fix that here quickly. Right, x was 4, not the h part. So we should have 4 plus h. So we should have had 16 plus h squared plus 8h. It doesn't change the numbers, I just had the wrong variable on here. So if we simplify it, we would have h squared plus 8h plus 16 minus 6 minus 10 all over h, and we're still doing our limits. As, again, I wrote the wrong letter. It should be as h approaches 0. Let's fix that quickly. And we should be good. So now you can see on the top we have 16 minus 6 minus 10. All of that would cancel out to 0. We have h squared plus 8h over h. We can cancel one of the h's. So all of this would simplify to just h plus 8. So now if we make our h 0, it works because we get just 8. And even if we would have tried it at any other step, if we would have plugged in our h of 0 here, we would have got 0 over 0, which doesn't work. Plug it in here, we would have got 0 equals 0. So we have to do the algebra to simplify it down to get things to cancel out. So in this case, our slope is 8. So our first one that we did, we had a slope of 4 at x equals 2. The one we just did, we got a slope of 8. Let's try one more, but use x of negative 1. So let's go right from this step here. I'll kind of finish it from here. So we'd have negative 1 plus h would be our substitution, minus 6. And if we plug negative 1 into the original, negative 1 squared is 1, minus 6 would be 5. So we should have the same kind of thing. So let's FOIL it out. We'd have h squared minus 2h plus 1 minus 6 minus 5 all over h. And again, you can see 1 minus 6 minus 5 would cancel. Sorry, I got a mistake here. Oh, I had a double negative. It should have been negative minus minus 5, which would be plus 5, so they do indeed cancel. And now our h's we can cancel as well. So our limit as h approaches 0 would be h minus 2. Plug in our 0, we get an answer of negative 2. I did that quick, but it should have worked out. So again, let's kind of think of it from a graphing perspective quickly. If we were to look at this original graph again, what we just figured out is at x of 2, so when x was 2, we had 2 negative 2, so that was somewhere down there. So that gave us a slope of 4. So you can see that that line was fairly steep with a slope of 4. When we went to x of 4, so that was quite a bit higher up here, that tangent line had a slope of 8, so that makes sense. It's steeper further up the curve. And then when we did x of negative 1, that was the last one we just looked at, and that had a slope of negative 2. So on this graph, if we went to where x is negative 1, that one gave us a slope of negative 2. So just by eyeballing it to the graph, the numbers and the negatives seem quite reasonable. So it's a little bit of work, but once you get the hang of it, it's pretty straightforward. You're just basically plugging in the numbers into the equation with your h, FOIL things out, simplify, and plug in your h of 0 for the limit. So let's try another example, but instead of doing the slope of the tangent line only, let's figure out the slope and also to get the equation. So we can do slopes of tangents, secants, or normal lines, and we can do the equations for each of those as well. So let's just kind of, it's sort of reviewing Math 10 as well, but let's kind of connect all these things together. So again, we have a quadratic, x squared minus x minus 12. The question is saying what's the slope at x equals 4, and then what would the equation of that tangent line be, not just the slope of it. So let's go through this one fairly quick. So our limit, again, let me rewrite our formula, was f of x plus h minus f of x all over h. So we want to take x plus h and plug that in the equation. So our x was 4, so let me just do that substitution first. It should be f of 4 plus h minus f of 4 all over h. I won't bother writing the limit part, we'll save a bit of time. So now we're going to plug 4 plus h into our equation. So we'd have 4 plus h squared minus 4 plus h minus 12. So that's our first equation. The second part, we're going to subtract f of 4. We could do it separately, but I'm just going to do it here to kind of save a bit of time. So plug 4 in, we'd have 4 squared minus 4 minus 12, all of that over h. So quite a bit of algebra, but again, it's just foiling and simplifying. So if we FOIL out the first one, we would get 16 plus 8h plus h squared. The second one is going to be minus 4 minus h. If we FOIL out that negative, negative 12 is good. And then the last one, we get 16 minus 4 minus 12, which is 0. So that that last part goes away, divided by h. If we simplify the top a bit more, we'll get h squared plus 7h, and 16 minus 4 minus 12 is 0, so all that goes away. Now if we divide by h's, we'll get h plus 7, and we do the limit again. Let me just put the limits back in, do the limit when h is 0, plug a 0 in, we get an answer of 7. So our slope of this equation at x equals 4 is 7. So that first part is probably the hardest part, and it's just doing the algebra. The equation now is going to be quite easy. If you remember back in Math 10, we typically write straight lines in the form of y equals mx plus b. So we have our slope of 7, so that's our m value. All we need to do is figure out what the y-intercept would be, and the simplest way to do that is just plug in some other coordinate for your x and y. And we can actually use any coordinate, but let's just use the 4 that was given to us in the question. So when we had an x of 4 and we plugged 4 in, that gave us a y coordinate of 16. That's what all of this one was, right? When x was 4, we got a y coordinate of 0. I said 16, but it was 16 minus 4 minus 12, which would give us 0. So we can actually use a slope of 7 and the coordinate for 0. And remember, that coordinate is just going to represent our x and y value. So we can plug those into the equation. So you'd get 0 equals 7 times 4 plus b. Rearrange that equation. B will equal negative 28. So our overall equation then should be slope of 7, and we just figured out our b value is minus 28, and we're done. So a good way to check this would be to graph your original equation on your calculator, graph this tangent line equation we just calculated, the 7x minus 28, put them both on your calculator, and you should see that at x equals 4, it should look like a tangent line. So again, I'm just going to estimate the graph looking something like this. And if we did the x equals 4, let's suppose 4 was down here somewhere, we would have an appropriate tangent line showing up on your calculator. So it's a pretty easy way to quickly check to see if you did things right or not. Let's try another example. We've looked at a few quadratics, so would this work as well if we had cubics? And the answer is yes. We just have to either FOIL things out more, or we got to deal with the binomial theorem or something just to make our life a little bit easier. But let's try it the same way. So this one we'd have limit as h approaches 0 of f of x plus h. I'll write the formula out again so we have it to follow. Minus f of x over h. So in this case we have x of 1. So we'd have, let me just kind of write it out again so we don't mess up. So we'd have an x of 1, so that would give us 1 minus 1 plus h cubed. Then f of 1, we just plug 1 into that. That gives us 1 minus 1 cubed, which is just 0, so that's nice. All over h. So even though it's a cubic equation, it still works out quite easily because everything's going to simplify quite nice. We get 1 minus 1, which is 0. H cubed would be all that's left over on the top. The other one is just 0, so that's gone all over h. So now we can simplify that by canceling out an h. So we'll just get limit of, as h approaches 0, of h squared. And if we plug a 0 in, 0 squared is 0. Okay, so if we were to actually look at this graph, let me just kind of sketch it quickly. If you remember a cubic graph going through 1, the graph is going to do a little S curve, something like that. And it does actually make sense. At x equals 1, we're getting a slope of 0. So that indeed it looks correct. So let's just do our tangent line equation now. So we have a slope of 0, and we can use that x of 1. If we plug 1 in, our coordinate was 1, 0, so let's use that as well. So if we plug that into y equals mx plus b, we get 0 equals 0 times 1 plus b, so we just get 0 equals 0, so b equals 0. So our equation for this is actually quite simple. Our tangent line is y equals 0, right? Because m is 0, b is 0, everything is 0. So that does sound right. Our tangent line would be just that horizontal line right along the x-axis, which would be indeed the correct slope and the correct equation of that tangent. So it's kind of a weird one because it's 0, but just to show you that it doesn't really matter if it's squared or cubed or whatever, the formula works just as well. Okay, here's another one. Got two different new things to it. The first part is it's a fraction, no longer a quadratic. We got a rational graph. And the second part that's a little different is we're looking for the normal line equation, but you'll see it's not that much different. So for the first part, again, let's do our limit formula. So we'd have f of x plus h. This time I should be able to do it all in one step. So let's try it here. So we'll have limit as h approaches 0 of f of x plus h. So we'd have x in this case is 2, so we'd have 1 over 2 plus h would be our first part. Take away f of x, so that's 1 over 2, and our bottom is just h. Okay, hopefully you can follow what I did there. I just kind of simplified the first step. And then now the next part is, how would we solve this? So because we have fractions, let's do common denominators. So we're going to have to times this first fraction by 2. We're going to have to times the second one by 2 plus h. So let's simplify that out. So the top we'd get 2 minus 2 plus h. I'll leave the brackets on there so we don't forget that. And then the bottom would be 2 times 2 plus h all over h. So if we simplify the top, that'll become 2 minus 2 cancels. We just get negative h over 2 times 2 plus h. And let's do our reciprocal. So let's flip our h over 1 to be 1 over h. And you can see, again, our h's will cancel. And I think we're done. So we have limit as h approaches 0, and all we get left over is negative 1 on top, and 2 times 2 plus h on the bottom. So if we plug our 0 in, we should be good. We get negative 1 over 4. So the negative 1/4 is our slope of the tangent line. So remember our normal line. So if our tangent is negative 1/4, our normal line is perpendicular and the negative. So it's the negative reciprocal. So you might forget this from Math 20, but let's just kind of do a quick review. Or Math 10, I can't really remember where you do it, but so if our limit of the tangent line is negative 1/4, so our tangent slope equals negative 1/4, the normal line is perpendicular to that. So perpendicular slopes are the reciprocal and the negative. So with the negative reciprocal, so you got to flip your fraction and do the opposite sign. So in this case, our normal line would be a slope of 4. After that, the rest is the same. So we use a slope of 4, and let's use our coordinate when x was 2. If we plug 2 back into the original, we had a y coordinate of 1/2. So now we can do our equation just like we did before. Put in 1/2 for your y, slope of 4, x of 2, solve for b. So that gives us 1/2 equals 8 plus b. If we subtract 8, that would give us negative 7.5 for our b value. So our normal line equation then would be 4x minus 7.5. And again, you could graph the original, and you could graph that, and you would see, instead of it being a tangent line this time, so this graph looks something like that. So if we looked at when x is 2, and we drew this tangent line equation, this 4x minus 7.5 would end up looking perpendicular to that, wherever that coordinate was. And I didn't draw this very good, but it gives you a good idea. Okay, so it does the exact same thing as we did for the tangent, except it's going to be perpendicular at that location. Let's do another example, just to kind of give you an idea of how this works for other kinds of functions. So this one is a square root function, so we need to do the same thing. So let's do our limit as f of x plus h. So in this case, x is 4, so we'd have 4 plus h under the root sign. Then our second part would be just root 4. And then on our bottom we'd have h. So these equations, when they're not quadratics, are a little bit easier to write, but the solving is a little bit more complicated. So the last one we did common denominators. Here we have roots, so we're going to probably have to do some rationalizing. So if I simplify this, we get 4 plus h on the top minus 2. That makes it a little bit easier. So now we need to cancel out this h idea. So we can rationalize the numerator, so let's times it all by root 4 plus h plus 2 on the top and bottom, and see what happens. So when we FOIL out the top, we would get root 4 times root 4 is just 4 plus h, so the roots cancel. The middle ones would cancel out because we'd have a plus 2 root and a negative 2 root, so we'll skip those, and then the 2 times negative 2 would give us negative 4, so that's good. And we don't need to actually do anything on the bottom. Let's just leave it the way it is, because you'll see that we'll be able to plug things in and solve it from here. So that's what our bottom's going to be as. You can see the tops, the 4 minus 4 would cancel, and that h that's left over on the top we can cancel with that h out front. So our final limit, let me just kind of write it in simplified form here, should be 1 over square root of 4 plus h plus 2. Plug our 0 in, we're good to go. So 1 over root 4 is 2. 2 plus 2 gives us a quarter. And again, we had to do this step because if we tried to plug a 0 in at any or h of 0 in at any location, we would have got 0 over 0 up here, or at any of these in between steps, they would all been 0 over 0. Till we canceled out that h, then we were good after that. So just like the last question, we have a normal line question, so our slope is a quarter. So that means our normal slope, our tangent was a quarter, so our slope of the normal line then would be the negative reciprocal, so it'll be -4 in this case. And let's use our starting coordinate of x of 4 would give us a y of 2. If we plug that 4 into the original equation, and we should be good to figure out our equation. So our y was 2, slope was -4, x coordinate was 4. If we can solve for b, so we get 2 equals -16 plus b, bring the 16 over, we get a b of 18. So our equation for the normal line should be -4x plus 18. And we're done that one. So we got one more. It's quite a long video, but it's worth us practicing a few of these, so when you get them on your own, you won't be struggling with them. So here's another rational. It's a little bit more complicated because we have x minus 5, but again, it's the same concept. So let's try to get at it here again with the formula. So we do limit as h approaches 0. This time we're going to do an x of 3. So we're going to have 3 minus 5 plus h on the top. Right, because remember we're doing x plus h. And then on the bottom we're going to have 3 plus h. Right, we don't have the -5, but we still plug in the 3. Then for our second one, that's the easier one. F of x is just plugging in the 3, so 3 minus 5 is, I'll write it out before we simplify, so we have 3 minus 5 over 3, and that's it. So it's a little bit ugly with this double x's, but it still works the same, right? Plug your, basically what we're doing is we're doing x plus h would equal 3 plus h, and then we're just plugging those into our x's. So we have 3 plus h on the top, so 3 plus h minus 5, maybe that would make more sense. Let me just switch these around so it doesn't look quite so complicated. Right, when we plug in the 3 plus h, we would have 3 plus h minus 5, and then on the bottom, plug the 3 plus h in, and it just stays as 3 plus h. So again, it's quite ugly, but if once we simplify it, it should work a little bit better. So the top would simplify to just h minus 2 over 3 plus h, and the second fraction is just -2 over 3. So that makes it fairly easy. Again, we got fractions, so let's try common denominators. So we'll times this fraction by 3, times this fraction by 3 plus h. And now we just have to FOIL things up. So the left side would be 3h minus 2, and on the bottom we would have, well, we'll just leave it like that. The other one we got -2, so we can flip those negatives to be plus. So that would give us plus 6 and plus 2h, and then our bottom would be just the 3 and 3 plus h. So I'll keep it separate for now, all over h again. So again, it looked, oh, I made a slight mistake. Let's just fix that. When I FOILed it out, I should have had 3h minus 6. Otherwise that screws things up, right? Because when we FOIL this here, we had 3 times h and 3 times 2. So that should work. Let's fix it from here now. So our top would simplify to 5h. And you can see the 6 minus 6 cancels, which is nice. Divided by 3 times 3 plus h. And the bottom, the divide by h, let's do our reciprocal again. So that'd be dividing, or timesing by 1 over h. So you can see our h's cancel, which is causing us our problems. And we're good. So our limit as h approaches 0 should be of 5 over 3 plus 3 times 3 plus h. Plug our 0 in, we get 5/9 should be our final answer. So we got a slope of the tangent line is 5/9. And let's go back to our original coordinate. If we plug a 3 in for x, we got -2/3. So we should be good to write our equation out. So we have negative 2/3 for our y, slope of 5/9, and x was 3. And we're ready to simplify that, so we get, it's fractions, a little bit ugly, but it should still be okay. We get 15/9, which would simplify to 5/3. So if we bring that 5/3 over, that should give us negative 7/3, if I did the math right. So our final equation should be 5/9 x minus 7/3. And that was a tangent line. Yeah, so we did it right. It wasn't a normal line question. So that's it. So quite a few examples, but I think it's good to see it several times to kind of get the hang of it. So our formula of f of x plus h, plug in the x value, put a plus h on with it, and then subtract your original f of x. And you can see in all of these cases, we always end up with just an h value canceling. Everything, all the other numbers seem to cancel, which is a good thing. If they don't, you did something wrong. And that's it. We're going to, our next unit now, we get into derivatives, and we're going to start with this same formula and see if we can kind of figure out a quicker way to deal with tougher questions.